And I would like to kindly introduce Daniel Pfarr from Dresden University, from the building construction group. And yeah, he is working there in this group as a scientist, of course, having experience in thin glass. And he will tell us about the influence of the Poisson effect on the determination of the bending tensile strength of thin glass. Daniel, the show is yours.
Thank you very much. Hope everyone can hear me. Thank you very much for the nice introduction. And I hope you are all good and survived the evening and enjoyed the dinner. Yes, today I would like to talk a little bit about thin glass. I think we had already a nice presentation about curved glass, which was still hot-bended when I remember it right. And today we can maybe explore a little bit about cold-bending thin glass and what challenges we have in this case. In particular, we as a research group, we are trying to determine the bending strength of thin glass, and that comes with some challenges. So let me directly jump into a short outline for today's presentation. I would like to briefly introduce thin glass and why it could be beneficial for that use case in the context of complex geometries. What challenges, what opportunities do we have there? Then I would like to go ahead with some mechanical testing basics, so the traditional way and maybe a new novel way how to test it. And then we are going to a physical phenomenon which is called the Poisson effect, which I want to explain briefly. And then we're going to the actually research topic of the paper we had as well, the finite element analyzed about the effect from the Poisson effect. I would sum up that with a short summary and an outlook at the very end. So let's talk about thin glass. I think common used glass thicknesses are 3 or 4 millimeter, but often 6 or 8 millimeter are being used in practice. And that's, I would say, kind of a comfort zone for everyone. And I remember the keynote 2 days ago, and I remember that someone talked about leaving this comfort zone. So if we would do that, so maybe we can work with 2 or 1 millimeter, or even thinner to 0.5 millimeter thick glass. Yeah, what benefits do we get here? I think one of the most, sort of the biggest benefit is the low surface weight. So we can design very lightweight structures, but also it has some benefits for environmental or environmental things like energy, resources and waste, and the footprint of the glass industry on these points here. And on top, I think connected to today's session, complex geometries, we have a very high shapeability of thin glass, so we can achieve very low radius with thin glass. So to sum it up, I would say it is a big opportunity, but of course it comes with some challenges. But let's talk about some positive points at the very beginning. So the opportunity for complex geometries. When we have a look into this graphic here, I have just drawn some glass thicknesses between 1 and 8 millimeters, and every glass pane is bended with a radius from 1 meter, so 1000 millimeters, and then on the left side you can see the stress distribution over the cross section of one glass pane. And you can I think very easily see that with the 8 millimeter glass sheet, this radius wouldn't be possible when you cold bended it. But as soon as we go down to 4 millimeter, then maybe with 2 or 1 millimeter, we get a significant reduction of the stress in the glass. On the other hand, when we turn it around and we want to keep a certain level of stress, for example, 100 Newton per square millimeters, then we can reduce significantly the radius of bending. So we're coming from 2.8 meters down to 350 millimeters for 1 millimeter thick glass. This comes, of course, with some challenges as well. So when we have this low geometrical stiffness, we have to think about new design concepts. How can we use it in the facade? Because, of course, we don't want that much deflection in the facade later on. I think there are basically two main concepts how to increase the stiffness of the glass. One is something like the thin glass composite panel. So we are using two very thin sheets of glass. We are dividing them by some kind of core, of a core structure, and then we have a very stiff and lightweight composite panel. One example just out of my research right now is this kind of thin glass composite panel where we have two thin sheets of glass and they're connected to a 3D printed core. Of course, it's not very transparent anymore, but we have some other benefits, which I don't want to talk right now, but I think another nice opportunity to increase the geometrical stiffness is to curve glass. So we get a higher stiffness with that, and of course we can combine it. And here a sketch from a colleague's research project. So we have two thin glasses. We can bend them like the radius I have already shown, and then they pour a polymeric core inside these two thin glass sheets. It's called the LOCA system in this research project, and then we have a very lightweight and fully transparent curved thin glass panel. So we can try to use thin glass in practice with new concepts, but more challenges are waiting with thin glass for us as researchers. So we want to determine the mechanical properties of thin glass. For example, mechanical properties like the bending strength. Traditionally, we are using a 4-point bending test. We have the standards for that. We are pushing the glass in the middle. We have two support rollers on the outside, and you can already see in this sketch that when we have very thin sheets of glass, we have that much deformation that they would slip out of the support rollers at the short edges. So we have to avoid this somehow. There are some new ideas. One of them is the so-called clamp bender, which I sketched here on the right-hand side. It's a much smaller test setup where we have two support rollers and the glass is clamped into the support rollers, and they have kind of a rotational angle. And with this rotational angle, we are loading the glass with a constant bending moment. In this case, we can keep the length of the specimen in the same like we did before, or we had an effective length in the 4-point bending test. And when we come to the calculation, we have this formula for the 4-point bending test. It's actually consists of 3 parts. The first is based on the Euler-Bernoulli beam theory. We have one part caring about gravity at the very end, and the first one, that's the so-called K factor, the correction factor, which I want to explain in a minute. But so we have these 3 factors here. When we're calculating the stress for the clamp bender test setup, then we are first calculating the bending moment, depending on the rotational angle, and in the second step, the stresses according to the thickness of the glass. Here, we are still based actually on the Euler-Bernoulli beam theory, but as you maybe noticed that we are missing here 2 parts, which is one, the gravity, but I would assume, okay, we can maybe ignore it for the moment, or at least for today's presentation, and maybe concentrate on the correction factor and how does it work for very thin glass and how to incorporate it into this formula. This is a diagram from the standard. And it's actually based on the research from Blanc some years ago. And here we have the correction factor, which we use for the calculation of the bending strength in the 4-point bending test. And you can see all the peaks over there from the different thicknesses. There are around 1.1, so that means 10 to 12%, which we add on the bending strength we are calculating already. Why is that the case? It is basically because of Poisson's effect, which I just want to briefly explain. Basically, it is a material physical phenomenon, which is the relation between the longitudinal strain and the negative lateral strain. So that means when we have glass with a Poisson number of 0.2, then every time we have a strain in the glass from 1 unit, doesn't matter how much it is, we have negative 1/5 in the lateral in 90 degrees direction. Why is that important? When we have our bending setup and we have a surface like that and we want to bend it, so we have actually only bending about one axis, but when we have very high or large deflections, then we get the bending over the second axis, like you can see here in the picture. And this leads to this kind of calculation. So the black line is the actual stress distribution in the cross-section. So we have the maximum at the edges because of this effect. But what we are actually calculating is the Euler-Bernoulli beam theory, which is without a width because it's a beam. And therefore we have a difference between reality and our calculation model. This is a previous research already done 1 or 2 years ago, and here we have already a numerical simulation with a 200 millimeter class specimen and different width and different load magnitudes, and we can already see there is a dependency on the ratio of length to width when we are calculating the stress. And so when we have very slender specimens, 200 to 20 millimeters, so we have quite low differences between the two calculation models. But when we have a larger surface area and aspect ratio from, for example, 1 to 2, then this increases quite high to round about 12%, which remembers me to the diagram before. For this setup today, for the finite element analysis here, so we set it up basically three hypotheses, which is the first one with decreasing width to length ratio, the deviation will increase. That's something we have already seen from the graph before. The second one is why shouldn't that be in the thickness as well? So we assumed that with decreasing thickness, the deviation will increase as well. And the third hypothesis was at the very beginning that when we are increasing the load, the deviation will increase as well, which comes from the diagram before again. But now we want to make a wider or open a wider field of view with different geometries, different thicknesses, and if there are any cross-links between them. So that's our finite element setup. Briefly explained, it is a quarter model, which you can see here. It is just a surface which we discretized with shell elements. We have a free translation in the x direction, which is the case for the clamp bender as well, at least for one support roller. The other ones are restricted, and then we giving a bending moment through this small alpha on the left-hand side through the rotational angle. And then you can already see here in this part, when we have the cross-section in the middle of the specimen, that we see some difference between the edge and the middle. In this case, it's the middle because it's only the half of the width from the specimen. And okay, there's already the difference we can see. And when we want to research that topic, then we have to define our variables. So what were we looking for? We at first changed the width between 20 and 100, the length between 100 and 400. So we have already 35 different combinations. And then we want to research the thickness as well. So we get 5 other layers on it in total. So we come to more than I think it's exactly 210 different variations in the finite element model. Of course, we want to incorporate the load magnitude. So this model we are researching, or we are evaluating on 6 different load levels between 10 and 60 degree rotational angle. When it comes to the result, then we can try to plot that much data into such kind of a heat map. Maybe I can simply or briefly explain what you can see on the left-hand side. On the y-axis is the width of the specimen. On the x-axis, the length of the specimen. We have 3 columns and 2 lines, and every quarter is now, in this case, glass thickness from 0.5 millimeter to 3 millimeter. And we are evaluating everything at 10 degrees rotational angle. And on the very top there we have the calculated stress from the Euler-Bernoulli theory. In the smaller brackets there we have the big value, which is the numerical value, and under the small number under it is the percentage deviation. I think that's too much number to overlook, so therefore we colored it with green and red color. So green color means a very low deviation. You can see it on a scale around about 1% is it starting, and then it's increasing up to 14% roundabout with indicated with the red color. And what can we see here? Basically, we can see that we have a small green area in most cases, and then a very narrow space, which is kind of a transition area. And then we are reaching the red area, but the red area is not increasing infinitely. It's kind of a plateau which we are reaching. So with comparing the width and the length of these specimens, we can say, okay, we can see the dependency of aspect ratio, but it's not only that we have to care about the aspect ratio between length and width, we have to take account from the thickness as well in this equation. So because you can see that it's changing over the thickness as well. But as soon as we reach this kind of plateau, in this case about 12 to 14%, we are not increasing it anymore. So we stay at this level. Yeah, well, the second part was to research the influence of the load magnitude. So for this example, we have only one specimen thickness, which is 2 millimeters, and we are evaluating it between 10 and 60 degrees. And we want to try now to see some connection between the load magnitude and the deviation between the Euler-Bernoulli beam theory and finite element model. And here we can also see that the green area will shift a little bit to the right down corner as well. So when we have higher load magnitudes, we have a bigger area where the deviation is high, between 12 and 14% again. So we can sum up here as well that the dependency of the load magnitude is still valid, but as soon as we go to higher load magnitudes, for example 60 degrees for the same thickness, we have a higher red area. That means it is more critical for higher magnitudes, but as soon as we get thinner with the glass, it is even more critical, let's say, because we have higher deformations in total. Yes, that's basically that for today. Let me just sum it up and give a short outlook to it. I would say the first one is that what I tried to emphasize in the very beginning, that thin glass opens up new possibilities for the building construction. We can achieve lower bending radius even in a cold spent process. We can achieve then complex geometries, and thinner glass leads then to higher non-linearities, which we have to take account into our research or into the calculation from the bending strength, but also in the design later on for our building. This is everything is probably attributed to Poisson's effect, which we tried to investigate a little bit more, and I think that should be into consideration in the determination of the strength of glass and also of the design in the design phase. Maybe we can restate the hypothesis. So I summarized the first two that we have with decreasing width to length to thickness ratio. I added the thickness here in this first. Again, the deviation will increase, but maybe we can here add a limit as well. So with a convergence at about 14%, so it's not infinitely rising. The second point is with increasing load, the deviation will increase. So we proved actually this for different thicknesses and in total geometrical properties as well. Maybe a short outlook. What's to do next, or what is still part of the research? So I think there's still a lack of incorporation of thinner than 3 millimeters. So we have already the diagram for 3 millimeters and thicker, but I think when we want to care about thinner glass in the industry, then we have to incorporate it somehow as a correction factor as well. And the influence of the Poisson effect on the spring-back forces, I think maybe there's some other lectures about it. So when we bend it, we get a spring-back force on the support what we are using, and the effect is of course in the middle of the glass pane as well. All right, I would like to thank our funding and all the project partners we have, and thank you very much for the audience. Thank you very much.